All right, hello and welcome. My name is Frank Regal, and alongside of me today is Christina Petlawani, and we're going to be presenting today on a human-robot teaming augmented reality tool called AugRE. AugRE, or Augmented Robot Environment, is a tool for supervising, coordinating, and communicating with robotic agents. Like I said, my name is Frank Regal, and presenting alongside of me today is Christina Petlawani. We're both PhD students at the University of Texas at Austin, majoring in mechanical engineering and working in the nuclear and applied robotics group with Dr. Mitch Pryor. To get started, we're actually going to show you a working demonstration of AugRE. The video you're about to see is a first-person view of a user wearing a HoloLens 2 augmented reality device. This video was actually submitted alongside of our accepted paper to the 31st Annual IEEE Conference on Robot and Human Interactive Communication. Alright, so as I mentioned earlier, AugRE is an augmented reality tool that allows users to localize with robotic agents in their space. Once localized, the users are able to see detailed information about that robotic agent. That detailed information, AR label, follows the robot as it moves throughout the environment. We've been able to scale this up to multiple robots and multiple HoloLens users. We've been able to do this both indoors and outdoors. We've also been able to give the robotic agents tasks to go ahead in the environment and look for, say, blue barrels or suitcases. When they find these blue barrels or suitcases, we've told them to send us a notification so that the user can provide feedback, get a better detailed view, or just dismiss the notification. We're using Azure Spatial Anchors to localize everybody in the team. We're going to get more into this in the software architecture part of the presentation. With a first-hand look at what AugRE is, we will now discuss into more specifics about the system itself. First, we will present the problem that AugRE is addressing. Then we will present a general overview on how the system works on the back end in the system architecture section. Christina will then present to you results from various performance studies we have performed on the system that address the scalability and latency. To close out the presentation, we will touch on some future work and acknowledgements. So what is the problem we're addressing with AugRE? First off, it's very difficult to collaborate with a heterogeneous team of robotic fleets. With a team of robotic agents, there's always communication bottlenecks. All the agents, being drones, mobile robotic platforms, static manipulators, they all have different diverse local localization techniques that they're using, and it's not consistent across the network. There's insufficient situational awareness and intent. When the humans are working next to robots, they're not really sure what's going to happen next with the robotic agent. Therefore, there's a need for an intuitive robotic interface to improve the human-to-robot ratio in human-robot teaming domains. Ultimately, we created AugRE as a launchpad to enable further research regarding human-robot teaming. AugRE is made up of multiple components, as you can see here. AugRE as a whole is a system made up of a HoloLens 2 augmented reality application, lightweight, ROS-based nodes running on robotic agents, and 3 servers that communicate constantly across the network with all agents connected to the AugRE system, as you can see there on the right. We'll dive deeper into the coming slide, but the 3 main services used to make the system function is a RoboFleet server, the Azure Spatial Anchor service, and an SQL database. These are all used to allow the agents to localize and pass real-time information across the network, as well as to stay persistent between multiple startups and shutdowns. The largest contribution and effort put into the AugRE system is the augmented reality application. This application was built using the Unreal game engine and deployed to HoloLens 2 augmented reality headsets. The purpose-built application consists of 3 major components. First is the Microsoft Mixed Reality Toolkit, or MRTK for short. This was used to display the holograms you saw in the video before. The second major development was the plugin for Unreal Engine. This plugin is a lightweight client that allows communication to and from the HoloLens with multi-robot ROS-based platforms. This open source plugin we developed is called RoboFleet Unreal Client and is based off the recently published RoboFleet Communication Manager from a neighboring lab here at UT, AMRL. We'll get into RoboFleet details later in the presentation, but essentially it's a more efficient communication method that allows teams of robots to communicate with little issue as opposed to other alternatives like ROS Bridge. The third major component of the application, shown there on the left, is the library of ROS messages AugRE supports. By adding common ROS message structs to the AugRE application, AugRE opens the doors for further development where multi-robot localization and communication is key. Now with the Unreal Engine application uploaded to the HoloLens is ready to go and to join the AugRE team. The robotic clients on the other end need a little bit of a configuration. For the robotic clients to join the human robot team, the mobile or static platforms need to only be a ROS-based system that can connect to the internet and are equipped with an RGB tracking camera like the Intel RealSense. After that, a few software packages need to be downloaded onto the robot. An Azure Spatial Anchor's ROS wrapper, a custom ROS package, and a RoboFleet client need to be installed and configured on the robot's hardware. With that, the robot client will be set up and will appear in the AugRE system. At launch of the programs on either the augmented reality headsets or the ROS nodes on the robotic agents, the agents start first by querying the SQL database for what are known as Azure Spatial Anchor identifiers. When the agents query this database and find identifiers, they go ahead and store these in memory, and then they query the Azure Spatial Anchor service that's hosted by Microsoft. This will be explained in the next slide. If they don't find any spatial anchor identifiers, the clients will go ahead and start creating Azure Spatial Anchors in the area around them. After those anchors are created, they'll go ahead and store that data in the SQL database to be later used in other app startups and shutdowns. Now with all the robotic agents and the HoloLens 2s holding this Azure Spatial Anchor identifier in their memory, they go ahead and query the Azure Spatial Anchor service. So what is this service? This service is a service offered by Microsoft. And essentially what it allows is for the localization between all the robotic clients and all the HoloLens 2 users within AugRE to know each other's relative position. What happens at AugRE's first initial startup within the environment is either a HoloLens 2 user or a robotic client goes around and places these spatial anchors. These spatial anchors are just data sets of RGB data that picks out certain features within the world that could be used again to localize. The features that are picked are parsed and stored in the Azure Spatial Anchor service in Microsoft's cloud. When the cloud receives it and processes it, it actually returns an Azure Spatial Anchor identifier to the HoloLens 2 and robotic agents. When the HoloLens 2 and robotic agents get this identifier, we have all those agents store that identifier in the SQL database that I just described on the last slide. So now that there was an identifier within the database and all the clients know that identifier, they go ahead and query the Azure Spatial Anchor database constantly as they explore around in the space. As they're exploring, the RGB cameras are actually looking for those features that identifier is associated with. When the features in the local time match with the features in the cloud, both the robotic clients and the HoloLens 2 users know that point in space. By knowing that point in space, and by every agent knowing that point in space, we're able to localize the relative transforms between all the agents in the AugRE team. Once an AugRE agent localizes itself to an Azure Spatial Anchor, the robot begins to publish location data. Each robotic client in the AugRE system runs their own SLAM algorithm on board. The location that each agent places themselves in their local map is the transform to the Spatial Anchor world frame. The transform location data is published out on a ROS topic. The RoboFleet client on the robot and the RoboFleet Unreal client on the HoloLens 2 users listen to this topic and publish the ROS messages to a RoboFleet server. The RoboFleet server manages what agents receive the messages. For AugRE, all agents connected to the system subscribe to all location data being published on the server at all times. So what is RoboFleet? RoboFleet is a recently published WebSocket-based robot communication manager that is designed for communication between multiple clients in large robotic fleets. This was developed by a neighboring lab here at UT Austin, AMRL, with Dr. Jody Biswas. In a recently published paper, they compared a communication manager to more common communication protocols like Bridge and prove it to be far superior. The major improvement this communication manager has over some of the others is that they are using a new serialization and deserialization methods published by Google not so long ago called Google Flat Buffers. With a RoboFleet client on all robotic agents, a RoboFleet Unreal client on all HoloLens users, and a dedicated machine hosting a RoboFleet server, AugRE proves to be a scalable system that sets up multi-robot localization and communication for large fleets. In the next few slides, Christina will present results of studies our team has performed on the AugRE system.
Thank you, Frank. When analyzing the performance of the system, we wanted to see whether the system was suited to the domains we mentioned at the beginning of the presentation. To do this, we looked at the performance of the system with an increased number of robotic agents and also the visual lag of the AR label above the robot, as shown in this little video here. For the system scalability, we looked at the latency and how the latency behaved as the number of robotic clients increased. We measured this in terms of round-trip latency, the time where a client would send a message through the system, the headset would register that message and send a response back, and then the client would receive the response. We looked specifically at the effect of the number of robotic clients and the publishing rate of those robotic clients. So with publishing rates varying from 5 Hertz all the way up to 60 Hertz in terms of the robotic clients. The latency of the system scaled linearly as the number of clients increased. Even at 50 robots, the latency of the system was still under 0.12 seconds for that round trip message. The effect of the publishing rate on our system was relatively minimal, as you can see that the timings are pretty grouped according to the number of clients with just a little bit of variation in terms of the publishing rate. The next performance metric we analyzed was the visual lag of the system. In order to do this, we recorded the visual lag along one axis. And to do this, we took video of the AR tag above the robot marker and analyzed that video to understand the displacement between the tag and the center of the robot marker in terms of pixels in the video. We converted this to a physical distance with the known width of the robot marker that was physically on the robot. From this, we saw that the lag decreased with the higher publishing rate of the robot. In terms of the 1 meter per second robot, it was from around 90 centimeters all the way down to around 70 centimeters. But the lower robot speed also had a significant decrease in robot lag, with the 0.5 meters per second robot speed decreasing from around 35 centimeters down to 30 centimeters. One thing we wanted to point out was what the visual lag looked like over time. So here we have the graph of the visual lag during one trial at 10 Hertz publishing rate. This trial shows the oscillation of the label, especially at lower publishing rates. And this is due to the label lagging behind the robot and then catching up when the system receives data from the robot client. So the higher publishing rates do really kind of improve this oscillatory lag and catch-up behavior of the robot AR label. We're really excited to use AugRE as a launch pad for future research, such as improving the human-robot interactions via eye tracking, to use the eye tracking data from humans in order to create a much more intuitive human-robot teaming interface. We are also investigating the system to create human-robot localization and navigation with landmark-based localization that will allow human and robot teams to localize and navigate an area together and interchangeably. We are also looking at dynamic environment multi-robot HRI to perform some control and to take over on the control scheme based off of the multi-sensory input occurring. So it may be better in order to use, for instance, at sometimes eye tracking, but maybe there is another control input that it is better to use at other times. And we want to use this to improve the use of remote telepresence, telerobotics, and especially teleoperation of robots. Here we just wanted to thank members of our team and people that we have collaborated with. Our current team is listed on the first line, and the second line are some people that have been on our team, including Dr. John Pelavanturk and Maxwell Svetlik, but also people that we've collaborated pretty heavily with in terms of RoboFleet from UT Austin's AMRL lab. We are also funded in part by this contract listed on the bottom line. In terms of our references, we just linked to the paper that will be published in the Roman conference coming up on AugRE, and also a paper published regarding RoboFleet. Thank you for listening to our talk, and we will now open up for questions from the audience.